This is 2.10 equilibrium. 6 points here. The first one is to demonstrate an understanding that many chemical reactions are reversible and to define the terms dynamic equilibrium, homogeneous and heterogeneous. Then deduce the qualitative effects of changes of temperature, pressure, concentration and catalysts on the position of equilibrium for a closed homogeneous system. Deduce the expression for the equilibrium constant Kc and its units for a given homogeneous equilibrium system. Relate the magnitude of Kc to the position of equilibrium and the extent of reaction. Describe and explain the conditions used in industrial processes. For example, the Haber process for the formation of ammonia and the contact process for sulfuric acid. And demonstrate understanding of the importance of a compromise between equilibrium and reaction rate in the chemical industry. So, many chemical reactions take place and reach completion. That is, they keep going until all the starting materials have been converted to products. So, for example, when magnesium is burned in oxygen, all of the magnesium is used up and all that's left is the product, the magnesium oxide. And you're familiar with that reaction. 2Mg plus O2 gives 2MgO. However, many reactions are reversible. And a reversible reaction is one which goes in both the forward and backwards direction. So, for example, the formation of ammonia in the Haber process is a reversible reaction. And here we see it, N2 plus 3H2. And then this double-headed arrow represents a reversible reaction. And that gives us 2NH3. So the nitrogen and hydrogen begin to react, making ammonia. And as the ammonia is made, it breaks down into nitrogen and hydrogen. And eventually, the rates of the two reactions will become equal, and there won't be any further change in the amounts of the reactant or product. And this then we call a dynamic equilibrium. And we said dynamic equilibrium has been established. So definitions here. Equilibrium is a reversible reaction in which the amount of each reactant or product remains the same. In a dynamic equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. A homogeneous reaction is one in which all the reactants and products are in the same physical state. A heterogeneous reaction is one in which all the reactants and products are not in the same physical state. So dynamic equilibrium can only be achieved in closed systems, that is, a system in which none of the components can escape. By opening up a closed system, conditions can be changed, after which the system can be allowed to reach equilibrium again. So the equilibrium position and the product yield of a system may be altered by the following changes. Changing the concentration of a reactant or product, changing the pressure of a gaseous equilibrium, or changing the temperature. And if we look at each of these in turn, look first at concentration. So increasing the concentration of a reactant or decreasing the concentration of a product moves equilibrium to the right in order to oppose the change made to the system. This increases the yield of the product. And conversely, if the concentration of a reactant is decreased or the product is increased, the equilibrium will move to the left, and this leads to a decreased yield of the product. Then changing pressure. So for an equilibrium system involving gases, changing pressure will affect the position of the equilibrium. An increase in pressure will cause the equilibrium to move to the side with fewer gas molecules in order to undo the external change, and a decrease in pressure will have the opposite effect. Changing temperature. Well, the effect of changing temperature depends on the enthalpy change for the forward and reverse reactions. Increasing the temperature causes the equilibrium to move in the endothermic direction to use up the extra heat applied. Decreasing the temperature causes the equilibrium to move in the exothermic direction to generate more heat. You also need to be able to work out the equilibrium constant for a reaction. So every reversible reaction has a characteristic constant called the equilibrium constant, which is expressed in terms of concentrations, and it's Kc. So it's a ratio of product concentrations to reactant concentrations and expresses the position of the equilibrium mathematically. So if we consider this reaction, A moles of A plus B moles of B gives us C moles of C and D moles of D. We can write the equilibrium constant Kc as Kc is equal to C to the power of C, D to the power of D, A to the power of A, and B to the power of B, where the things in the square brackets are concentration, and then the powers are simply the number of moles from the balanced equation. So in the square brackets means the concentration of substance A. So A in square brackets is the concentration of A measured in moles per dm cubed. So the units of Kc depend on the values of A, B, C and D in the expression. So if A and B is equal to C plus D, then Kc will have no units, in which case you just write the answer no units afterwards. So like say the answer was 72 no units. Okay. So for example, one of the key reactions in the contact process is the reversible homogeneous reaction between sulfur dioxide and oxygen to form sulfur trioxide, and it's given here. 2SO2 plus oxygen gives 2SO3, and you see that they're all gases. So the equilibrium constant, Kc, would be SO3, concentration of SO3 squared from this 2, the concentration of SO2 squared from the 2 here, and just the concentration of oxygen. There's only 1 mole of it, so we don't need to add anything there for a power. So the units then, mole dm to minus 3 squared over mole dm to minus 3 squared times mole dm to minus 3. Okay? And what that means is if we cancel out the 2 of them, we end up with 1 over moles per dm cubed, or moles to the power of minus 1 dm cubed. And you need to do that for the units for any Kc question. So the value of the equilibrium constant gives an estimate of how complete a reaction is at that particular temperature. So very large values, greater than 10 to the power of 10, indicate the reaction is almost complete. Large values between 10 to the power of 4 and 10 to the power of 10 indicate the equilibrium position is far to the right, the product side of the system. Intermediate values, so between 10 to the minus 4 and 10 to the power of 4, indicate the reactants and products are present in similar amounts. And small values of Kc, so between 10 to the minus 10, 10 to the minus 4, indicate the equilibrium position is far to the left on the reactant side of the system. Very small values then, where Kc is below 10 to the minus 10, indicate the forward reaction is not noticeable. Now, in industrial chemistry, when you're devising multi-ton processes, industrial chemists must consider a number of factors such as reaction kinetics and equilibrium when deciding on the optimum reaction conditions. So for example, considering the Haber process, and we've seen it already, N2 and 3H2 gives us 2NH3, and when we look at delta H, it is negative because that's an exothermic reaction. So from a kinetics perspective, high temperature and pressure leads to a faster reaction. However, from an equilibrium perspective, whilst a high pressure favours the forward reaction, it's costly to maintain and the pipes and equipment are expensive. So the forward reaction, though, is exothermic, so a high temperature reduces the yield of the product, but a lower temperature would make the rate very slow. So reaction conditions are chosen which are a compromise between the cost, the kinetics, and the equilibrium considerations. And in this case, for the Haber process, it's 400 to 450 degrees C and 200 to 250 atmospheres with the use of an iron catalyst. Then for the contact process, where we're looking at this reaction of sulfur dioxide and oxygen giving us sulfur trioxide, again, it's an exothermic reaction. So a low temperature favours the forward reaction. However, this would give a slow rate of reaction. High pressure favours the forward reaction as there are fewer gas molecules on the right hand side, and high pressure is expensive to maintain. So in this case, the compromise conditions are a temperature of 450 degrees and 1 to 2 atmospheres of pressure, and a vanadium oxide catalyst is used. So vanadium oxide is a solid, so it's a heterogeneous catalyst as it's in a different phase from the reactants. And as you know, a catalyst does not have any effect on the position of equilibrium.